Okay, so for part A, we needed to measure the resistance in the same row and also in the same channel and two different channels using jumper wire. So if we measure the resistance in the same row, we found out that the circuit is closed, but if they are in two different channels, the circuit should be in the open state. And the exception for that is if we use jumper wires across two different channels, we will get a closed circuit because the two channels is connected through jumper wires. So this is for part A. And for part B, here we measured the nominal values of ohms or the resistors, which was written in the boxes. Then we used the DMM to measure every single resistor in the same row, and we found out that that the difference is between these values, which is plus or minus 5%, and these are the values. So this is basically for part B. Then we moved on to part C. And now for part C, using the power source here, we measured the maximum and the minimum values of the voltage output, which was using the DMM, of course, and we got these values. And for
part D, we plugged in a resistor in the middle space, and then a wire from the DC output through these two inputs, and then we use the DMM to measure the voltages directly with the resistor that's in the middle one.
Yeah, without the jumper wires.
Without the jumper wires, and then again by removing the resistor, putting it on this side of the board, and then connecting them with jumper wires, which is indirectly. Measured the voltage and amps again, and it came out as the same, which it should be the same. I think there was a small difference because the wire might increase the resistance a bit, but it's basically the same thing. And for part E,
and for part D also we needed to measure the current across 5 resistors, and due to overloading in the circuit using this DC power source, we used Ohm's law to measure the current values, and we compared the nominal resistance and the measured resistance, and also we calculated the percent difference between those two values, and all the values make sense depending on the amount of resistance.
So for part E and F, we were supposed to study these two machines. They're basically the same thing, but this one is a bit more complicated than this one. This is like a simplified version of this.
And the input should be here and the output should be here.
Basically, they are supposed to give outputs, waveforms, graphs that look differently with each button you press.
The sine wave, the square wave, ramp, and the pulse.
Whichever one you need. The other one is basically the same thing, just a bit more complicated, but it can also give an output where the other one can't.
And yeah, we're using the main input, which is this one, the X and Y.
And this is the output wire, which we will need to plug in if we want to get a graph from this.
Okay. And for part 2, we used ORCAD to create both of these circuits. So here is the first circuit we created using ORCAD, and this is the Zener diode, and this is the transistor. Also, this is also part 2, the second section of part 2. We created it using ORCAD, which is the same circuit design as this one.
For part 3, we would demonstrate the non-ideal power source or voltage source. So we have two, one with the internal resistance and the other without. So we did it in ORCAD simulation, and this is without the internal resistance. We got a voltage source and a resistance load, and the other one is with the internal resistance. Okay, so the analysis shows that without the internal resistance, we get the voltage source equaling 1, the same as the voltage source. The output should be the same as the source.
The out, yeah.
But when we put in the internal resistance, which is right here, we get the voltage output as 0.6 millivolts instead of the voltage source, which is 1. And we have also constructed the circuit here, but this one is a different one. We constructed the circuit, and we have also shown we got the results exactly the same as the analysis. And these are the data for it. And for 3.2, which is basically the same, but has a different circuit.
I think not 3.2.
Yeah, we did the analysis too for it, which is this one. This is with the internal resistance, but I will show you first without. Okay.
So this is without the internal resistor.
This is 16 ohms.
Yep. We get 0.6 or 0.76 volts. Okay. And now let's use the
With internal resistance,
internal resistor.
which is 10 ohms.
Yep. So 10 ohm resistor with a 16 ohm resistor. And this one is the internal resistor.
Yeah.
So let's try this one. We're getting a 0.47 volts.
0.47 millivolt. Volts.
Yeah.
And it's lower than without the internal resistance.
Yep, perfect. And this one, let's use this one, which is 30 ohm. You can replace it with the 16 ohm.
Oh yeah, that's because we're, yeah.
Okay.
Because our total is 0.6.
So this is the internal resistor of 10 ohm, and this is the resistor of 30 ohm. And the value of it should be 0.67 volts. And for our last part of 3.2, we measured the loading effect here. So this is the output voltage without using an internal resistor, and this is with using an internal resistor. So we measured the loading effect, which was the actual voltage value minus the measured output value over the actual voltage value times 100%, which will give us a value of 92% of a loading effect.